event-driven architecture, orchestrating cloud-native workflows. So this is the trendy and important topic right now, right? So I'm super excited to explore it. And it is all about using events, signals that something has happened, to orchestrate workflows and create responsive, scalable systems. So let's embark on the journey together and unlock the potential. This is Mostafa Mahmud, working as a software engineer at Station 23. Also proud to be an AWS community builder in the serverless category for 2023. Excited to be here today as we explore the fascinating the world of event-driven architecture. Uh, Throughout my journey as a software engineer, I have had the privilege of working on projects for leading brands in the various industries. Welcome to my session on event-driven architecture. Today, I'll cover the basics of EDS. I will break down what they are and the key concepts that make them tick, why use the event-driven architecture and how to use it, orchestration and versus choreography. I will compare these two approaches to coordinating tasks in the event-driven architecture. I will discuss some key factors to keep in mind when designing your own event-driven systems. I'll share some pro tips for building robust and scalable event-driven. Yeah, I'll show you the live demo for error handling workflows following the ADS architecture. And I will wrap up at the end of this session with some helpful resources to keep your EDA journey going. So let's jump right in. So in today's dynamic world, applications are constantly responding to users' actions and system changes. So event-driven architecture places events at the core of application development. So modern applications are inherently event-driven. Events are everywhere. So for example, a customer placing an order, a social media post being created, or a sensor reading being uploaded. So event-driven architecture places these events at the core of application development, transforming them from a byproduct into a powerful communication mechanism. So service publish events, something happened, and subscribe to relevant events. React to what happened, leading to loose coupling and faster development cycles. So there are some cloud providers like AWS, Azure, GCP. So they offered a comprehensive toolkit for building serverless event-driven architecture. Services like AWS Lambda, AWS, Amazon Kinesis for event streaming, Amazon SNS, SQS, etc. And Azure provides Azure Functions for serverless and Azure App Service for managed serverless. Also, GCP provides Cloud Functions and so on. So there are some core values of event-driven architecture. These are all about building complex applications. Unlike traditional architectures that constantly ping for updates, event-driven architecture reacts to events in the real time. This shift unlocks some amazing benefits. Independent feature development, effortless feature integration, loose coupling, and modularity. So imagine microservices like building blocks. With EDA, teams can work independently on services that publish and subscribe to events. This reduces dependencies and lets you roll out new features much faster. And effortless feature integration, adding new features becomes a breeze, right? So no need to modify existing applications. New features can simply subscribe to existing events, like plugging into a real-time information stream for innovation. Event-driven architecture's asynchronous processing lets your system handle massive volumes of events without bottlenecks. Plus, if one service fails, it doesn't bring down the whole system, increase resilience for your applications. Services communicate through events, leading to cleaner, more modular code with less complex dependencies. This makes your application easier to understand, maintain, and scale as your needs grow. It enhances flexibility and maintainability by reducing the impact of changes to one component on others. These are the core values working together to create more flexible and robust foundation for your applications. So why the organizations follow the event-driven architecture? So there are some strong points. So real-time responsiveness. Event-driven architecture enables applications to detect and respond instantly to events triggered by users and systems, providing a seamless uh, integration and interactive user experience with under low latency. So this real-time responsiveness enhance user engagement and satisfactions. Event-driven architecture facilitates seamless integration with external systems and services. This extensibility allows for integrating additional features and services to enhance the application's functionality. Finally, the we get the opportunity to minimize the resource consumption. Unlike traditional request response model, event-driven architectures minimize resource consumption by responding only to events, reducing delays and improving server efficiency. This optimization enhance overall performance and resource utilization, right? There are some key concepts of event-driven architectures. Building blocks that work together to create a powerful communication mechanism. Let's break them down. So there are some key points. Events, event producers, event consumers, and event brokers. So let's say events is signals that something has happened. An order created event or a payment received event. These events are like little snapshots on in time, describing a specific change that has occurred. They are also immutable, meaning once created, their content cannot be altered. This is especially beneficial in complex systems because it eliminates the need to constantly synchronize data across different components. And event producers, these are the entities that create and publish events. Think of them as heralds announcing something newsworthy. Event producers can be various components like UI, microservices, IoT devices, and other AWS services, or different kind of. Uh, it can be SaaS applications also. And even consumers on the receiving end, we have even consumers that there are the downstream components that get triggered by events. An event can have multiple consumers, each reacting in its own specific way. Event consumption can involve starting workflows, running analysis, or updating database based on the receiving event. And another thing is point event brokers. Imagine event brokers as the communication hub. They act as intermediaries between producer and consumers. So uh, it manages the publishing and subscribing of events. They buffer communication, ensuring producer and consumers don't need to be in sync with each other. Event brokers come in two forms. Event routers and event stores. Event routers that actively push events to their subscribed consumers, and event stores where consumers can pull events on demand. So by understanding these key concepts very well on your way to leveraging the power of the event-driven architectures in your applications. Let's talk about the coupling. How tightly concerned different parts of your application are. On one end of the spectrum, we have tight coupling. So let's see how this plays out. Development challenges, scalability issues, reduce fault tolerance. So there are many complexity. So look at the image on the slide and imagine a traditional e-commerce application where order processing, billing, shipping, and inventory all rely on synchronous calls. A single service failure could disrupt the entire flow. This is where event-driven architecture comes in. EDA promotes loose coupling, where components communicate through events instead of direct calls. So this approach offers a significant advantage, which we will explore in the next slide. Uh, I mean, it is considered the power of events. So let's see how the event-driven architecture addresses the challenges of tight coupling with loose coupling. Imagine components communicating through independent events instead of relying on the direct calls. In loose coupling, components publish events about their state changes without requiring immediate response from others. Think of it as sending out messages as announcements. Components declare what happened. So, and interested parties can react accordingly on their specific way, own specific way. So, in an event-driven approach, components only need to be aware of the events they publish and subscribe to. not the internal working of other components. As long as the event format remains consistent, changes in one component won't affect other component. Idempotency is the crucial part. So, idempotency, imagine pushing a button and action happens exactly once. Even if you pass it multiple times, there's the essence of idempotency. Ensuring an operation produces the same outcome after the first successful execution, regardless of the retries. So, why the idempotency is the important here? So, this property becomes especially important in the event-driven architecture. So, when dealing with the retries, a common practice for handling potential failures. For example, let's say a lambda function triggered by an order placed event. So if the function encounters an error during the initial execution because of server failure, because of internet issue or anything else, the Lambda service might automatically retry the invocation, right? So without idempotency safeguard, this retries could lead to chaos, complex, serious issue, and duplicate orders, corrupted data, and anything else, you name it. So how to achieve idempotency here in this scenario? So we can include a unique identifier within each event as an idempotency key. This key allows the system to recognize if an event has already been processed, preventing unintended consequences from retries. So by incorporating idempotency, you ensure data consistency and reliable operations in your event-driven architecture. So, so there are some common patterns of event-driven architectures. So first of all, point-to-point messaging. Actually, it's a fundamental pattern. So now, it is sending it's like sending a message with a specific recipient in mind. So this is the essence of point-to-point messaging. In event-driven architectures, messages are often delivered asynchronously, meaning the sender uh, doesn't wait for a response before continuing. Messaging queues like this on the slide act as the middle ground, like mailboxes. So producers, senders, put messages in the queue, and consumers, like receivers, retrieve them when they are ready. So on their own specific way on when they are ready, right? So this asynchronous approach ensures smooth communication, not a uh, uh, enforced communication. So even if the receiver is temporarily unavailable, plus these queues act as buffers, preventing message loss if the receiver is overloaded, right? So and there are several services that can be used as message queues. Popular options include Amazon SQS, Simple Queue Service, and Amazon MQ, powerful tools for reliable message delivery. And secondly, publish subscribe messaging. So publish subscribe messaging is the unlike point-to-point messaging, where messages are targeted to a single consumer, but publish subscribe messaging allows messages to be sent to multiple subscribers, right? So instead of using queues, this pattern typically employs event routers such as topics or event buses. Examples of services supporting this pattern include SNS, simple notification service. So simple notification service is used for topics. For the event buses, the Amazon Event Bridge is used. So in details, to say, topics function as simple hubs for distributing messages to subscribers. Event buses can provide more complex routing based on the message attributes. So here in the slide, we see the blue and green role with message 1 and message 2 accordingly. So the event bus will check the rules, attributes, and then send them to the targeted consumers, subscribers. So yeah, now I'll talk about the event streaming. uh, it involves continuous flows of events or data, providing a way to abstract producers and consumers. Unlike pub-sub messaging, where messages are pushed to customers, in event streaming, consumers usually pull for new events. So consumers maintain their logic for filtering events and keep track of their position in the stream. Event streams can consist of individual events like location updates in a ride-share app, or data points collected over time from IoT devices. So data source can be anything like logs, business metrics, any other AWS services, right? And here in the middle point, data streams actually a subset of event streams interpreted over time and are often used for normally real-time data analytics applications or data persistence use cases. So there are services supporting event and streaming performance, like Amazon Kinesis Data Stream and Amazon MSK. I mean, Amazon managed streaming for Apache Kafka. This is called the Amazon MSK. Okay, so this is the choreography and orchestration. This is the common pattern. Now, choreography and orchestration are the two models for the how distributed system, distributed application services communicate with each other. So in the choreography pattern, we can say communication happens without a central controller. Events flow between service and services, and each service reacts to events independently, not dependable with others. On the other hand, orchestration involves a central coordinating service that controls the interaction and order of service invocation. So we can say that while choreography promotes decentralized and flexibility, orchestration provides centralized control and coordination. So many applications use a combination of both choreography and orchestration, selecting the model that best fits the which a specific use case actually. So there are different use case vary different usage pattern. So uh, next in this slide, I'll talk about the bounded context actually. So bounded context is a fundamental concept in the I mean domain-driven design, representing a core pattern in its strategic design approach. Triple-D's strategic design section is dedicated to handling complex models and teams efficiently. The in the choreography pattern shines the communication between bounded context. I mean, as the same concept is uh, in the slide, the image, there are two bounded contexts. I mean, sales context and the support context. So, in the every bounded context has the multiple microservice, multiple services. So, I mean the bounded context and the one domain, and one domain have the multiple services. So, for example, in the e-commerce example, the order service and the inventory service. The order service focuses on creating, placing order, emitting, and order placed event with the relevant details. There are many events, but one domain, order service. This is the bounded context. Another bounded context is the inventory service. I mean, a separate bounded context subscribes to the events and manage stock levels. So, importantly, both services can be made aware of others' internal topic, but the order service simply sends the events and the inventory service reacts accordingly. This approach fosters loose coupling, scalability, and flexibility as well. So event buses such as event breeze can be used for the choreography. Okay, and now I'll talk about the orchestration in details. So orchestration is the another key pattern in the event-driven architecture. So it's a particularly well suited for scenarios within bounded context where you need to control the order of service calls, manage state, and handle errors or retries effectively. So to solve this problem here, orchestration comes in. So for example, in the slide, you can see the document processing in the insurance claims in this example. So consider the document processing bounded context with the insurance claims application. This context receives the document uploaded event, and orchestrator service within the context first classifies the uploaded document using a document classifier service based on the classifications, I mean driver license or car image. So the orchestrator directs the workflow. If it's a driver license, the extract driver license info, I mean detail service parse the information regardless of the document type. The extracted data is updated in a database. Finally, the document processing domain emits the document accepted event with all the extracted details. So orchestration provides a centralized control mechanism for complex workflows. and it ensures proper service execution order, state management, and error handling also. So leading to a more reliable and maintainable applications. So here the some services uh, to execute these workflows. I mean AWS step functions and Amazon MWA. I mean Amazon managed workflows for Apache Kafka. So choreography and orchestration are complementary. I mean, not mutually exclusive. So even many applications benefit from using both patterns for different scenarios. There are a few main points when both together come. I mean, producer orchestration, consumer orchestration. Now here some key points comes in. Emits producer in the producer emits events via event breeze, demonstrating the choreography approach. And in the same line, the producer orchestration part utilizes step functions within its bounded context for orchestrating, I mean, API calls to Amazon API gateway. On the receiving end, the multiple consumers subscribe to events via choreography approach. I mean, SNS topic, app client, SQS, Lambda, Amazon API gateway, application load balancer, and and in the same receiving end, one there is one consumer orchestration. I mean, one consumer also leverages the step functions for internal orchestration within its bounded context, and it comes the next the same process. So the previous slides explored the choreography and orchestration independently, but however, their true power lies in their ability to be used together within the same applications. So, as illustrated in the enhanced example, a producer can emit via event bridge for the choreographing consumption by various services. Simultaneously, the producer itself can leverage step functions within its bounded context to orchestrate API calls. So on the receiving end, consumers can subscribe to events choreographically, while one consumer might also employ step functions for internal orchestration within its own bounded context. So we have the key takeaway by that I mean by strategically combining choreography and orchestration, we can gain a powerful toolkit for building scalable, loosely coupled, and adaptable event-driven architectures. So this approach empowers us to effectively model complex workflows and the interaction within our applications. There are few combining patterns. One of them fan out, I mean distributing a single event to multiple subscribers, while individual patterns can address specific needs. I mean the true power of event-driven architecture lies in combining them strategically. So uh, fan out pattern is a fundamental concept, and actually and it allows a producer to send a single message to multiple of subscribed consumers. This approach is particularly useful when uh, sorry. So let's say, for example, let's say social media notification system where a user uses post creation triggers fan out events. This event might be of interest to various consumers, such as a service for generating activity feeds, another service for sending push notifications to followers, so and a service for timeline updates. So the fan out pattern ensures all these consumers receive the same event, enabling them to perform their task efficiently. Now I'll talk about the event filtering and routing. So it directs event to specific targets based on the predefined criteria. It improves message relevancy for consumers and reduces unnecessary processing. I mean, event filtering and routing is a cornerstone of the flexible and targeted communication in the event-driven architecture. It enables us to define criteria that determine which events get delivered to specific consumers. This ensures that consumers only receive relevant to their dominant functionality uh, to escape to remove the unnecessary to remove the getting the unnecessary messages. So event breeze can filter and route events based on predefined criteria, ensuring only relevant events reach specific consumers. And now I'll talk about the event and message buffering. So it utilizes queues as a buffer to manage the message volume for downstream consumers. It ensures messages are delivered reliably even if consumers are temporarily unavailable or overload. So here the event and message buffering pattern comes in. It promotes asynchronous communication and improves overall system resiliency. So now I'll talk about the workflow orchestration, and it is the more important uh, on this session. This slide demonstrates how step functions can be used to model a KYC workflow, promoting an event-driven approach with loose coupling and low-code integration via event-based service. So in the step number one, so we can say uh, new account request event, right? So the process begins with the account system publishing and event signing a new account request. This event triggers the KYC workflow execution within a dedicated KYC service. And the second step, KYC verification. So this might involve tasks like identity verification and risk profile assessment. So and then step three, identity check completion, and step four, conditional events based on the risk assessment. I mean, after risk profile assessment, the workflow publishes one of the two events depending on the outcome. I mean, whether account approve or account reject. So, uh, and step five, event consumption by downstream services like both account and consumer service domain. There are two domains domain actually. So I've defined roles on the event bridge bus to process this KYC workflow. KYC are my outcome events. I mean, the accounts domain likely handles the account creation or further processing based on the account approved event, and the customer service domain might be notified for potential outage to the customer based on the account rejected event. So in this from this example, we have the summary. You have the benefits of this step function workflow in the event-driven architecture. So this approach promotes loose coupling, as services don't rely on direct communication. They simply uh, publish or subscribe to relevant events on the event bridge bus. And another thing we can see in this example, the modular workflow step function orchestrates the KYC process in a defined sequence, ensuring a clear and maintainable workflow. And also low code integration, utilizing event bridge simplifies integration between the KYC service and other domains requiring minimal custom code. So this is the low code integration actually. And by leveraging step function event bridge, so here we can see the financial institutions can establish the robust and scalable KYC workflow and ensuring regulatory compliance and efficient customer onboarding. Right. So far, we have explored the various aspects of event-driven architecture. Now, let's introduce AWS step functions. Actually, it's a serverless orchestration service that can seamlessly integrate with event-driven architecture. So, there are some key components for step functions workflow. I mean, state machine, states, and task states. So, state machine represent your entire workflow. There are few types of state machines. I mean, choice state, parallel state, and so on. Especially a series of event steps here comes in. So and states, another component is states. Is step within the workflow is called a state. Another component is task state. This state represent units of work executed by other database services, such as invoking the Lambda, and task state can interact with any other database service like SQS, SNS, SES, and API gateway, and anything else. So the core benefit of the step function is the visual workflow design, and the graphical console provides a more clear view of the application's workflow, making it more easier, making it easier to understand and manage complex event-driven processes. So use cases for the step functions could be maybe machine learning model workflow, ETL workflows, long learning workflows, and so on. So step functions provide two main ways to interact with other services within our workflows. I mean, SDK integration and optimized integration. And there are two types of workflows in the step functions. I mean, standard and express. So standard execution is the time to up to 1 year, and exactly once workflow execution for this type. And the pricing is also per state transition. And to say use cases for this standard is ideal for long running or auditable workflows where execution history and visual debugging are crucial. Express workflows, at least once workflow execution. And the execution time is up to 5 minutes. And to say pricing, the per number and duration of execution, and the use cases of this express workflow is the perfect for high event rate workloads such as streaming, data processing, and IoT data ingestion, etc. To choose the right workflow type between the standard and express workflows, yeah, actually it depends on the specific needs. So standard workflows are ideal for scenarios requiring uh, strict execution order, auditability, and long running process. On the other hand, express workflows excel in the high throughput scenarios where rapid event processing, streaming, data processing, IoT data ingestion is the essential here. All right, so let's dive into some practical applications for the AWS step functions. So first of all, function orchestration. So imagine a complex workflow like processing a customer order. Step function excels at orchestrating these tasks. So you can define a sequence of lambda functions where each function performs a specific steps. So calculate total, update inventory, trigger shipment, etc. So step function visuals these interactions, ensuring everything happens in the correct order, and you can easily verify the flow. And on the branching with choice state, so step functions allows you to incorporate decision making into your workflows. For instance, in a credit card application process, a choice state can evaluate the request credit limit. If it's below a threshold, the application can be automatically approved. However, existing the threshold can route the application for manual review by a manager. So here's the branching example. So and for the error handling, so step functions offers mechanism to handle errors smoothly. For example, a customer registration where the chosen username is unavailable. A retry state could automatically attempt registration with a slightly modified username a couple of times. Alternatively, a catch state could intercept the error and suggest alternative usernames for the customer to choose from. So human in the human integration, step functions can even integrate human integration steps. Suppose you have a process requiring manager approval. So here step functions can utilize callbacks and task tokens to send the task to lambda function that might notify the manager and wait for their decision before continue the workflow. So this is useful for scenarios when human intervention is necessary. So there are other use cases: parallel processing, dynamic parallelism with map step. Parallel processing, the imagine converting a video file to into different resolution for various devices. The parallel state allows you to distribute this workload amongst multiple lambda functions simultaneously. Significantly, it is speeding up the transcoding process compared to doing it one resolution at a time. And dynamic parallelism, it works with map state. Map state empowers us to process collections of items in the parallel using lambda functions. A good example is an order fulfillment scenario. So where you might have multiple items that need to be prepared for shipping. The map state can trigger lambda functions to process each item concurrently. Checking availability, gathering the item, packaging it for shipment, etc. So now let's see the demo on error handling workflows, and then I'll back to the slide. So error handling custom error functions has the throw new error. For this is a custom error. Step create completed. In the step functions, we have two state machines. Error handling state machine with retry. In the resource sections, the copy I have to copy the ARN and to paste the if the ARN is mismatched, the error comes in. The error handling parameters. we can check the execution, input and output, and the step functions workflow. So this is a custom error, and here the output that comes from the lambda functions and start execution. So to view the custom error message, the start execution in the graph inspector pane and the review the input table. So now handle the failure using catch. So here task map and parallel steps may contain a field name catch, start execution task and error. So copy and paste the lambda ARN of the error handling state machine with catch lambda. Now custom error and next workflow step in the custom error fallback. So when it catches this error, it passes flow control to the fallback step, custom error fallback. So select the custom error fallback state in the graph inspector pane and clean the input and output. So custom error fallback message, this is a fallback from the custom lambda function exception. So this workflow exactly as expected. I mean, it should show this is a fallback from a custom lambda function exception, and it does. Use the catch a timeout error and error handling sleep 10 function lambda. So copy ARN of this lambda, put the ARN in the state machine where I want to execute the error. I mean, sleep set timeout function. Error equals state timeout and next timeout fallback. Next event timeout fallback. So let's see what happened. Click save and execute. Accept the default input and click start execution. To view the input of the fallback state, select timeout fallback state, timeout fallback state, timeout fallback state. Input and output, this is fallback from a timeout error. It works perfectly as expected. Okay, and after finishing this demo, I'm deleting this spec. All right, let's talk about the best practices and while considering building EDA applications. So firstly, event storming, it's a collaborative technique that helps us visually map out a system behavior and identify those crucial events in the event-driven architecture. The idea is to bring together stakeholders from different areas of the system. We then facilitate a workshop where we can all together to visualize and discuss the system's events and actions. The main goal here is to get everyone on the same page, everyone on the under the same umbrella about how the system works and pinpoint those critical business events. ECST events, I mean ECST event carried state transfer events. Notification events are like concise messaging informing consumers that something. ECST events like a definite approach. They act more like more data carriers containing a richer payload with more information relevant to downstream consumers. So imagine a user placing an order. In an event-driven architecture, we can create an order-placed event to notify downstream systems like inventory management or payment processing that a new order exists. So notification events essentially act a messenger, informing interesting consumers that something has happened. But on the contrary, ECST events take more have the more information, more metadata in the full details data. And another best practice is the conformist pattern, is the straightforward approach for consuming events in the event-driven architecture. In this pattern, downstream consumers directly utilize the events published by producers. I mean senders without any modifications or transformations. And another point, ACL, I mean protecting domain boundaries. Let's say two bounded contexts with distinct data models, business logic, and potentially even language. And ACL acts as a mediator between these contexts. So it provides a translation layer that safeguards data from one domain from corruption or misuse when consumed by another domain. And another best practice is the OHS, I mean shared language for communication. uh, uh, Pattern OSA is open host services patterns. I mean, it promotes communication between bounded contexts by establishing a shared public language. I mean, this language acts as a common ground for the data exchange, defined through agreed upon interfaces, contracts, or schema, or anything like this. And another perspective is the event fast thinking. Remember, event identification and design are the ongoing process, right? So regularly revisiting your events, ensuring they remain relevant to involve business events and business as well as business needs. Final best practice of the ordering and order and unordered events. Not all events need to arrive in the specific sequence, but however, some scenarios require a guaranteed order for events to be processed correctly. And understanding this distinction is vital for designing your EDF effectively. And for example, a scenario where an order updated event must be processed only after the corresponding order created event arrives, right? So to achieve this, you can leverage service that guarantee event order. Here are a couple of options on AWS. I mean, Kinesis data stream order is preserved within the message in a shard, and Amazon SQS FIFO, I mean first in first out. So events are delivered within a message group ID in the order they were sent. Here are some helpful resources to keep your learning journey on event architectures going. I hope you found it informative, and feel free to reach out if you have any questions. So yeah, have a good day.